Hey, hi, welcome to the day 5 of the DP workshop. Today we're going to talk about iterative coding of DPs and we're going to solve certain problems from the forms that we have learned and actually go ahead and try to understand how to code them in an iterative fashion if required, because there are certain class of problems that require you to code things in iterative manner, number one. Number two, sometimes it's easier to write recursive code, sometimes it's easier to write iterative code. So once you get expertise in recursive thinking, I would suggest you to also learn the iterative model because it will help you sometimes to solve certain questions very fast. Number three, there are certain space optimizations and time optimizations that are designed in a way that it can only be used on iterative problems. So that's why iterative coding becomes essential to know for someone who wants to get far in DP, right? So we will learn that today, and we're going to learn why it's working and how to kind of convert whatever we have been thinking recursively into an iterative code. Okay. So what is the main idea for this particular thing, first of all? So let's say you have been writing something like, let's say DP of some level, right? We have been writing something like this quite often, right? Let's say some X, some Y, right? And from this, we have been going into a transition, let's say like DP of, let's say level plus one, some A, some B, right? Let's say DP of level plus one, right? C, D, something like this, just two different transitions, okay? What is this essentially talking about? It's saying that to compute the answer for this particular state, okay, we need to know the answer for these things first. So while we were writing recursive codes, if the answer for this particular state was already available, we returned directly, or else what we did, we computed this, okay. It in turn called the recurrence of these two states. If it was calculated, then it will return directly, or else it will compute and return, okay. When we are trying to do iteratively, we will go through every state only once. So the difference between recursion and iterative fashion is that we have to pre-decide an order in which we will go through the states so that we can compute the answers directly when we reach a particular state. So let's say when we reach this particular state over here, right, we want to make sure that we have already calculated the values for these two states so that we can merge them very efficiently, let's say, to get the value of this one. So the main idea of iterative coding is to ensure that you have a way to go through all the states such that when you reach a state X, and let's say X needs the state Y and Z to be to compute its value, these are already available to you. Okay. So we have to devise a way in which we can iterate over the states in such a way. That's all there is to iterative coding. You will see how we do these things as we go on, but like this is the main idea. Okay. Now let's go forward and let's try to like kind of see certain problems. So the first problem that we will start with is this one. I particularly tried to take new problems so that you also get a flavor of trying new problems in the video, as well as to understand how to code them in an iterative fashion if you have to do though. Okay. So the first problem that we're going to take is this. There is two piles A and B stones with A and B stones in each. Okay. So there are two piles. There are A stones on one, there is B stones on one. So when you say stones, it's like there are B number of stones, there is A number of stones. In one turn, there are two players who are taking turns and playing game. In one turn, the first player, let's say, any player whose move it is, can take any number of stones from one pile. Okay, any player can take one move from one pile, any number of stones from one pile, or he can take equal number of stones from both the piles. He or she can take equal number of stones from both the piles. These are the two different options that we have. Now, a player who cannot make a move or who cannot pick any stone, if both the stacks becomes empty, then that is you can think of it as a losing state then, which means in that case the like whoever is playing right now is going to lose. Okay, so we need to decide like given a configuration A comma B, we need to tell who is going, like is the player one going to win or player two going to win. Okay, so this is, let's say, the problem. How do we solve this one? So just to give you a quick example, let's say we have some two stones over here and one. So if the first player goes and like he takes both two stones from one, the other player will come and take one stone from the other pile, and the first player now has no move. If the first player comes and takes one pile from this side, one stone from this side, then the other player will come and take two from this one, because he or she can take any number of stones from one pile, right? So that will leave the other player losing again, the first player losing again. If the first player comes and takes one from this, so you will be left with 1-1. The second player can come and do this move, take equal number of stones from both, so it will convert it to 0-0, and then the first player will lose, right? So this is how the transitions would work, and in this case, it turns out that we can try and model this particular thing in DP problem, right? So which particular form do you think this particular question would lie in? Since this is a player game, we are going to go into form 5, which is game DP. So the step 1 that we have for the framework is find out the form. So this is form 5, game DP. And we now remember the structure of form 5, that there is the state. For this, we need to decide losing and winning, and depending upon what moves we have, can we reach a losing state or winning state? Depending upon that, the answer will be computed. Step 2, what is the state? Step 2, to find out the states, right? In this game, there are like just 2 numbers given. The current stone piles, the current number of stones that are there in the 2 piles. And whenever you make a move, you can like change the things, but it will always be 2 piles with certain number of stones. So the state can be equal to dp of the configuration of the game can be represented very well by the number of stones that are there currently in the 2 piles. Let's say I'm gonna say x and y, which is gonna tell me the number of piles in number of stones in the first pile, number of stones in the second pile. Okay, and the return value would be, is this winning for p1 or for player playing now? Okay, that's the state. How do we decide the transition for this? Let's go and do the transition part as well. What is the transition? As given in this question, you can take any number of stones from one pile, take equal number of stones from both the piles. So from dp of x comma y, I can go ahead and try to change the stones over here. So I can go to dp of, let's say, some z comma y, where z is in the range x minus 1 till 0. I can go to 0 stones. I can go to 1, 2, 3, 4 up till x minus 1. Note that I will have to at least take 1 stone out of it, right? Or I can go into dp of x remains same. I move this first operation on the second pile. So some z, where z is going to be equal to y minus 1. Okay. Or I can take equal number of stones from both the things. So maybe dp of x minus k comma y minus k, where 0 is less than equal to, where 1 k, like you at least take 1 stone, so k is at least 1, and at max it can be min of x comma y, because if there is no stone in a particular pile, then you cannot take more than the number of stones that are there in a certain pile, right? So that is the number of like things that you can take. So this is like k is the number of stones you're picking up. This is the z is the stones after you have picked up. So you can think x minus z is the number of stones you're picking up, something like that, right? So these are the different transitions. These are the different configurations that you can move to. And for this particular state, if any one of them, so by default, this is a losing state. But if any one of these states is a losing state, then this will convert to a winning state. That's the logic, right? If any one of these is a losing state, then you can push your opponent to a losing state. So you are going to win. So by default, in game DPs, we initialize things with losing state. And if you can throw your opponent in a losing state, then you are winning, right? So this is how we kind of go ahead and try to see the transitions in this particular problem. Let's do a quick time limit check as well, just to see if you guys are able to understand the time limits of the problems as well or not. What is the time limit of this particular thing, or like complexity check? What is the complexity of this particular problem? Number of states is going to be like the initial number of stones is a and b. So it's a for x. This can be 0 to a. This can be 0 to b. So it is order a into b. Number of transitions. Over here there is like x number of transitions, which can be at max a plus. So these are all different transitions. You can go to any different z over here for in the range over here for range y, which is up till b, plus b transitions plus min of a plus b. Okay, this is the number of transitions over here. So in total, this is going to be equal to order states into transitions, state into 1 plus transitions, but in this case, this is over here. So states a into b into, this is minimum is always less than the sum. So we can omit this off if you want in order notation, and you can write a plus b. Okay, so this is the total time complexity of this particular idea. Okay. Now to code this particular problem in a recursive manner, this would have been enough, and we could have written a recursive code. But the way I want to do it is, I want to do it in an iterative manner. So there is going to be one extra step that we do, okay, that we need to determine is order of computation. Okay, you find out order of computation. And how do you find out order of computation? This is very, very important. Okay, right, let's try to see what exactly does a x comma y depend upon. Okay, so let's try to pictorially think that x comma y is this particular cell in the whole 2D matrix. So you remember, right, we are going to save this dp into a 2D matrix. So let's say this x comma y is a 2D matrix. Okay, and the x comma y is going to depend upon, you can, like, let's say this is the row x and this is the column y. Okay, and this is, let's say, 0 comma 0 0 cell. Okay, 0 comma 0, this is the matrix. Okay, the dp matrix that we're going to create. Though in general we have the matrices in an inverted way, you can think it this way as well. I would suggest, if you think matrices in this way, I would still keep that notion for you. Let's say this is the 0th row, this is the 0th column, and this is the cell x comma y. Okay, this is the row number x, this is the column number y, this is the cell, and this is where we are going to save the value. Okay, now to compute this particular value over here at this cell, we need to know certain other values, right? What is the other values? So for this cell, we need to know the value of z comma y. So some z comma y, where z is less than x, is this part of the thing, right? Z is less than x, the row is less than x, and the column is equal to y. So this part, x comma y, which is this part, and you remove equal number from both the things. So x minus 1 comma y minus 1, x minus 2 comma y minus 2, x minus 3, this something like this. So these all, like, cells is what, these all states is what this particular state depends upon. Okay, so these all states is what this depends upon. So we need to make sure that when you are looping through the states, when you are looping through different possible values of x comma y, you need to iterate in a manner that when you reach this cell, you need to have these values readily available for you. The values over here should be available in the dp array that we are trying to create. And a quick way that you can do for these kind of problems is just to iterate over in this manner. See, when you reach this cell, all these are already available, all these are already available, all these are already available. So we can go in a row major order to compute the values of the dp, because at any particular cell you will have all the cells that we need the correct value of already computed. Okay, so that's the thing that we will try to see. We will go 0 to x for 0 to a for x, and then for each x, like for each x, we will go y in the range 0 to b. This is something we can do. Okay, and we'll compute the answer for each one of them. So this is the next step, the fifth, like an addition step that we do before we write it iterative. Okay, so that's the whole, like, mental idea that we go through. I mean, I understand this is the first time you're seeing this, and this is not a very, very easy problem. But again, let's try to code this up in both the recursive and iterative way so that you can kind of understand what we are trying to do. Okay, so let's get into a bit of coding. So if I have to, like, kind of solve this problem in a direct way, let's say I'm gonna write the recursive way, and I'm gonna do the iterative way as well. Okay, so that you guys are absolutely clear on what is happening. So let's say I'm gonna have up till 1000 only. Okay, int a, b. So these are the two different cells, two different piles that we have, and we need to return the value whether it's like cout recurrence of a comma b. Okay, but before that we need to compute the dp. So if we had to do it in the usual way, we would do it this way: size of dp, right? And then we call the recurrence, then we write the pruning case, then we write base case, then we write things like cache check, then we write compute, save and return. I mean, by this time I should try and create a template of this out of this recurrence so that I don't have to write it every time. But yeah, Next is this pruning case is over here. So we don't really need to prune anything in this problem. The base case would be if you have x is equal to 0 and y equal to 0, in that case we are going to get, what are we going to get? In that case, this is a losing state, we cannot play, so return 0. This is a base case. Okay, now if you want to do a cache check, very simple way to do that would be if dp of x comma y is not equal to -1, which means we have computed it, return dp of x comma y. Okay, now to compute, we are going to assume that this is a winning state, this is a losing state, so this is a losing state, but if we can go to any losing state, then this will become a winning state. That's how we do form 5 problems. So now we go through all different transitions that we can go. So first is we can reduce x to any different z less than it. So for integer z is equal to 0, z is less than x, z plus plus. Okay, if recurrence of, if this is a like losing state, if z comma y is equal to 0, if this is a losing state, then I can push my opponent to a losing state, so I am gonna win. So answer equal to 1, and we can keep it 1 over here. We can even break it over here because we just want to find the first one. I'm gonna just quickly copy this up and use it for y as well, and for the other thing as well, for the like equal from both the things as well. If it is less than y, so we can also reduce the y directly from this one, and if it is a losing state, then we can go there as well. And the other thing that we can do is we can go to min of x comma y, right? We can remove one stone and we can go up till min of x comma y. And if we remove this many stones from both of them, and if it's a losing state, then we are still in a winning state, right? This is the 3 different options. And finally, like if any one of them makes a 1, it's the winning state, so that's fine. And finally, we're gonna return dp of x comma y equal to answer, and that's the whole dp that is there, right? This is the whole recursive code for this particular problem. Now, if I had to write this in an iterative manner, how would I do that? This is the whole recursive idea. This is going to be like a into b into a plus b, but how do we write it in an iterative manner? That's the next thing that we're going to learn. The way we do that is we kind of go over here and try to decide how do we loop over this x and y, all these states, all these variables, so that everything gets already computed in a dependent manner. So instead of this memset and all, okay, what we're going to do is we're going to create a, so instead of going to a particular x and y, we're going to do is this: x is equal to 0, x is less than equal to a, x plus plus. Okay, for integer y is equal to 0, y is less than equal to b, y plus plus. Okay, this is what we are doing right now. Why are we writing this? Because the discussion that we had, in this particular order, if you are going first through all the cells over here, x equal to 0, then x equal to 1, then x equal to 2, at any point in time, whichever cell you come across, like let's say you come across this cell, okay, you know that these cells are already computed at that point in time. So it is fine if you like loop it in this order. You can understand what I mean by this soon enough when I code it up. So now we are at a particular cell x comma y. Okay, now we have to compute the value of x comma y, dp of x comma y over here itself. The way we do that is we write the base case over here. I mean, it's actually very similar to what you would write in like a recursive code, but it's just that you need to, like, instead of writing a recurrence, just copy this part over here and paste it over here to certain sense. Okay, like that's the main thing that we do over here in these kind of problems in its true logic sense. If x is equal to 0 and y equal to 0, then instead of returning, we're gonna save dp of x comma y equal to 0. Okay, we're gonna save the value of it's a losing state over here itself. Okay, now we don't need any cache check over here in case we are not doing it recursively. Now to compute the answer for this particular state, what we're gonna do is we're gonna like keep an answer just as we do it, and instead of calling the recurrence, we're gonna just simply call dp of z comma y. This is the only change that happens. Okay, the only change that is going to happen is this. Okay, and there is no returning in the question. Now this is what is there. This is the whole iterative code for this particular problem. What we have just done is that instead of like letting a recursion decide how to find out the value, we are looping through in an order of the states such that whenever you reach a particular state, let's say some x comma y, all its previous things that it depends upon with whatever like values it needs, they are all saved in the DP array already. So we don't need to go over and like ask the recursion to check if it is not computed and compute it. We know for a matter of fact that since by the way of ordering and computation of the states, we have saved it, so we can directly use the DP array instead of recursion. Okay, so that's the main idea that we use for such problems, and like just convert the whole thing over here. Instead of calling the recurrence, we are now going to call the array itself, and that is going to give us the answer that is required. And we can simply return, like now we know that every cell saves the correct value, so we can return this over here. Okay, so this is how we solve a particular problem in an iterative manner. I just took out everything that is there in the recursion and just kept this DP array over here. You can even convert this DP array. You can keep the DP array inside the solve itself, but I mean, I just keep it global just to keep it simple. Yeah, this is how we can do this one. And this is how we can solve this particular problem in an iterative manner. Now there is no recursion to this code, right? And it's just a simple loop through all the states, but in a way that when you reach some a comma b, x comma y, you have all the dependency resolved. All the states that it requires are already saved in its correct place. Okay, so that's how you write iterative codes for such problems. And this is one problem that we solved. In the next video, we're gonna take up another problem and solve it in an iterative. First solve it in a recursive manner and then convert it to an iterative manner. Reason being, we're gonna do it for multiple problems is that first of all, you are gonna learn more and more ideas to solve problems. And second thing is that you need to know for different types of forms how to write codes in a neat way in an iterative pattern, right? So that's what we are gonna do in the next few videos. Okay. Also, if you have been liking this particular series of DP Workshop, make sure to like the video and leave a comment on what do you want on more in this particular series, because I understand that the workshop is fine, but on the channel I can put up more and more content even after this. So if you think that something would be relevant for DP or something more, feel free to like add it on the comments, or even just a comment that, hey Vivek, I enjoyed the content, is also something I would love to know. Okay, so that would be all from my side for this video. In the next video, we're going to take up more and more problems. This was the first video where we understood the new step of ordering the computation and converting the code. Just taking out the recursion and putting it over here. The transitions and everything remains the same. It's just that we now don't depend upon recursion and just loop. Okay, so that's all for this particular video. See you in the next one. Bye bye.